Imagine taking, like, a small screwdriver to the phone in your hand right now.
Yeah, just prying it open.
Exactly. You pry off the casing, you peel back the screen, but instead of finding a rigid green silicon motherboard packed with all that microscopic metal architecture, you find a weird, flexible, waxy, red-purple plastic film.
Right, it looks almost like a dried smear of lipstick.
Yeah, exactly like that. So what if I told you that cheap piece of plastic runs 250 times faster than the most powerful Apple chip on Earth and could theoretically hold a charge for, well,
I
weeks?
mean, it sounds like science fiction. Or, a scam.
Oh, completely.
But the theoretical blueprint for that exact device is sitting right in front of us today. It represents a complete abandonment of how we've built electronics for the last 70 years.
Welcome to the deep dive. We are tackling a massive, mind-bending stack of source material today. It centers entirely around a startling 2026 paper by George James Dukas titled Galactic Organic Computer.
It is a heavy read.
It really is. Our mission today is to unpack a single staggering claim: the idea that the silicon age is effectively obsolete. We're going to explore how a mathematical equation, one that was actually written to explain the center of an atom, accidentally provided the blueprints for an ultimate organic smartphone.
And along the way, we might just have to rethink materials, science, quantum computing, and, well, a few other things we will definitely get to later.
Oh, we are getting to the weird stuff later for sure.
Definitely. The scope of Dukas's paper is enormous. It's a really dense text, bridging nuclear physics, organic chemistry, and computer engineering. The core proposal is a 1 terahertz organic computer. But the key to the whole thing is that it is derived entirely from the golden ratio.
The mathematical constant known as phi.
Right, exactly.
I want to start with the physical reality of our current devices, just to understand why a smear of red plastic is such a big deal for you, the listener. Like, when I play a heavy video game on my phone, the back of the device gets incredibly hot.
Oh yeah, totally.
Sometimes to the point where the screen dims to protect itself. Why are we still dealing with that if our chips are so advanced?
Well, it is because of the material itself. A modern computer chip is essentially a microscopic city made of silicon.
Right.
To do any calculation, you have to push electricity through that city. You have billions of tiny gates, called transistors. And in traditional silicon computing, a transistor operates by brute force.
Brute force.
Yeah, you apply a voltage, usually around 0.8 volts, and that electrical pressure basically forces an electron channel to form. It literally forces an opening in the silicon lattice so current can flow. That is your on-end state.
Okay, I follow.
And you take the voltage away, the channel vanishes, and that's your OF state.
So every time my phone calculates something, it's forcing a tiny gate open and closed.
Billions of times a second. But silicon is a rigid crystal. It doesn't want electrons just flowing through it. It naturally resists.
And in physics, electrical resistance becomes heat.
Exactly. We literally fight the physics of the material to make it do what we want. We have hit a wall where making the gates any smaller or pushing the electricity any faster just generates too much thermal energy. The chip melts.
Okay, so silicon is basically a massive microscopic traffic jam. How does this red-purple plastic solve the traffic jam?
It changes the mechanism of the gate entirely. The source text introduces 2 foundational chemicals that make up this plastic film.
All right, what are they?
The first is called NTCDA, and the second is fluorinol.
Are those highly exotic, unpronounceable lab creations? Do they require, like, a particle accelerator to make?
No, not at all. NTCDA is actually a commercially available dye.
Wait, really? A dye?
Yeah, it's heavily used in the OLED screens of modern televisions and smartphones already. It forms a flat molecular base. The fluorinol, on the other hand, acts as a molecular hinge attached to that base.
A hinge.
That's right. Together, they create an organic transistor that operates not by forcing an electron channel through a rigid wall, but by using molecular torsion.
Torsion, meaning twisting.
A physical twist, yes. The paper details that if you apply a highly specific pulse of electricity, exactly 0.62 volts, you aren't pushing a wave of electrons through the material. You are physically twisting the molecule at the fluorinol hinge.
That is wild.
In its resting state, the OF state, the molecule is mostly flat. The text gives the exact angle. It is a twist of just 0.0138 radians. In this position, it acts as an insulator. Electricity cannot pass.
Like a closed door.
But when you hit it with that 0.62 volt pulse, it snaps. The hinge twists to an angle of 0.0528 radians.
Okay.
That slight physical contortion suddenly turns the molecule into a highly efficient conductor. The door swings open, The electrical signal passes through, and then the molecule springs back flat.
Okay, wait, I have to stop you there. Let's unpack this. I can buy the idea of a tiny molecular door, but you said earlier this thing runs at a terahertz.
I did.
That is a trillion cycles a second. If I bend a piece of plastic back and forth even 20 times, it gets hot. If I bend it 100 times, it snaps. How are we physically twisting a billion plastic molecules a trillion times a second without the entire film just bursting into flames or vibrating itself into dust?
That is the exact problem researchers have been trying to solve for a decade. The text actually brings up a really fascinating piece of history here.
Oh, what is it?
Around 2015, researchers at Samsung spent about $1 billion investigating these exact same OLED films. They wanted to make organic processors.
Okay, so they were already trying this.
Yeah, and they managed to get them to work. Somewhat. They achieved what they call decent mobility, but they could only get the molecules to switch at about 1 kilohertz.
1 kilohertz, 1,000 times a second.
Right.
1,000 is a long way from a trillion. What was stopping them?
Friction and disorder. The Samsung films were essentially thrown onto the surface haphazardly.
Like just randomly painted on.
Pretty much. Imagine trying to get 1 million people to do a highly synchronized complex dance routine, but they're all packed tightly into a mosh pit, facing different directions, standing on uneven ground.
Oh, that sounds like a disaster.
Right. When you tell them to spin, they hit each other, they scatter energy, they generate heat. The molecules degraded rapidly because of all that friction.
So Samsung had the right idea with the twisting molecule, but they just couldn't organize it.
Exactly. The author of our source text, Dukas, solved the mosh pit.
Ow.
He realized you need perfect geometric alignment. The text describes a specific process. You apply the film onto a gold surface, specifically configured as an AW111 surface, and you anneal it at 120 degrees Celsius.
What does annealing actually do in this context? Is it just baking it?
It is a very controlled heating process. When you raise the temperature to exactly 120 degrees, the molecules gain just enough thermal energy to jiggle around.
Okay, they jiggle.
Right. And the gold surface underneath them isn't smooth at the atomic level. It has a specific, repeating hexagonal pattern. Because of the shape of the anti-CDA and fluorenyl molecules, as they jiggle over that gold template, they naturally slot into place.
Oh, wow.
They self-assemble into a perfect crystalline lattice. When you cool it back down, they are completely locked in.
Oh, like shaking a box of eggs until they all settle perfectly into the grooves of the egg carton.
A phenomenal analogy, yes. Once they are perfectly aligned in this lattice, the physics change completely. They don't hit each other when they twist anymore. The entire layer moves in perfect resonance.
So the friction is gone.
The twist requires almost zero extra energy. The text states it snaps between the AW-N and AW-FF states with a conductance ratio of exactly 15,127 to 1.
That is a very specific number.
It is. And because of this perfect frictionless geometry, the switching speed jumps from Samsung's 1 kilohertz straight past megahertz and gigahertz all the way to 1.02 terahertz.
So it isn't fighting physics anymore, it's just naturally vibrating.
Exactly.
But wait, how did Dukas know to use exactly 0.62 volts? You mentioned Samsung was throwing $1 billion at this. Were they just guessing the voltage?
They were trying empirical testing, basically trial and error. They were testing 1.5 volts, 2 volts, 5 volts, trying to force the twist.
And hoping something worked.
Right. Dukas didn't find the 0.62 volt threshold in a chemistry lab. He found it mathematically. That threshold was predicted by the literal shape of atomic shells.
The shape of atomic shells. Okay, you are going to have to walk me through this one. How does the inside of an atom dictate the voltage of a plastic smartphone processor?
This is the bridge the paper builds between vastly different fields of science. To understand the plastic, we have to look at the math, and it all rests on one simple quadratic equation.
Let me guess, it involves phi.
Yes, x squared minus x minus 1 equals 0.
I vaguely remember my high school algebra. That equation solves to give you the golden ratio, right?
Right.
Phi. About 1.618. We see it in sunflower seeds, nautilus shells, Greek architecture.
Yes, that is the one. They also formulated a highly specialized nuclear equation based entirely on that golden ratio. It looks incredibly complex. It involves phi raised to various powers based on an integer k, representing different shells.
Okay, keeping up so far.
Originally, this equation wasn't about computers at all. It was published to predict nuclear magic numbers.
What makes a number magic in an atom?
In nuclear physics, the nucleus of an atom is made of protons and neutrons. But they aren't just a clump of marbles.
Right, they are quantum particles.
They behave as standing waves of energy, and they pack together in distinct layers, or shells. Physicists noticed decades ago that when a nucleus has certain specific numbers of protons or neutrons, like 2, 8, 20, 28, or
Mm.
50, the atom is incredibly stable.
Like hard to break apart.
Exactly. It takes a massive amount of energy to break it apart. Those are the magic numbers.
Because the shell is perfectly full, like a completed puzzle.
Yes. Ducas's phi-based equation was able to predict these exact magic numbers and even calculate the precise binding energies of light nuclei, like oxygen-16 and helium-4, with 2.6% accuracy.
That is pretty accurate.
It proved that the center of an atom holds together based on the geometry of the golden ratio.
Okay, that is fascinating for a particle physicist, I guess. But what does a perfectly packed oxygen nucleus have to do with twisting OLED plastic?
Here is the massive leap the paper makes. It argues for a universal scaling law.
Meaning what?
The paper posits that electrons, the particles orbiting the outside of the nucleus, which dictate all of chemistry, obey the exact same phi shell-filling rules as the protons and neutrons inside the nucleus.
Wait.
The standing waves pack together using the same geometry, regardless of scale.
So the rule for the center of the atom is the rule for the outside of the atom.
And therefore, the rule for how atoms bond together to make molecules. When Dukas analyzed the structure of our organic computer molecules, he found they mapped perfectly to his nuclear equation.
Are you serious?
Yes. The flat part of the die, the NTCDA, perfectly matches the mathematical parameters of a shell, where the value K equals 10, meaning it holds 123 available energy states. The florinal hinge perfectly matches shell K equals 8, holding 47 states.
So let me push back on this. You're saying the exact same math that prevents an atom from flying apart is the math that dictates the shape of this plastic molecule and how a cell phone processor switches.
That is the claim.
Is it possible this is just a mathematical coincidence? The human brain is great at finding patterns, like seeing faces in clouds. How do we know this isn't just pareidolia with numbers?
A crucial question, really. The difference between pareidolia and physics is falsifiable prediction.
Okay, what did it predict?
The text introduces a universal constant derived from this math called epsilon Ntor. It's a tiny number, exactly 0.0007542 electron volts. Dukas showed that this exact mathematical constant dictates the binding energy of an oxygen nucleus.
Right.
Then he took that same constant, plugged it into his equation for the molecular hinge, and it spit out the exact voltage needed to twist the florinal molecule.
It spit out the 0.62 volts.
Precisely, 0.62 volts. It mathematically predicted the exact electrical threshold that Samsung couldn't find with $1 billion of trial and error.
Oh, wow.
But to your point about coincidence, the paper goes further. It claims this geometry obsoletes traditional quantum chemistry.
How so?
Currently, if a pharmaceutical company or a materials lab wants to know exactly how strong a chemical bond is between two atoms, they have to use a supercomputer to solve what are called electron repulsion integrals.
Electron repulsion integrals, that sounds intensely complicated. What is the supercomputer actually doing?
Think of it like trying to predict the flow of traffic at a massive city intersection. But the catch is that every single car magnetically repels every other car.
What a nightmare.
The math is a nightmare of probabilities. Supercomputers have to crunch billions of these interactions, and it takes days just to simulate simple molecules.
Because electrons are negatively charged, they all hate each other and want to push away, but they're trapped in the atom, so the computer has to guess where they all end up.
Yes. But Dukas bypasses the probabilities entirely. By treating the molecule as a perfect phi geometric shell, his single equation predicts the exact bond energy of a hydrogen molecule, which is 104.2 kilocalories per mole.
Just from the equation?
Yep. It predicts the exact tetrahedral bond angle of a methane molecule, 109.47 degrees, instantly, on a piece of paper, no supercomputer required, and no empirical fudging to make the numbers fit.
So if the math was a hallucination, the hydrogen bond prediction would be wrong. The methane angle would be wrong. But they match reality perfectly.
The geometry is an inevitability. The molecules self-assemble into that perfect plastic lattice on the gold surface, not by magic, but because the golden ratio is the most efficient way for standing waves of energy to pack together in this universe.
If the math is that perfect, let's talk about what happens when you build a machine out of it, because understanding this universal geometry isn't just an academic exercise.
I'm from it.
The practical specs of what this paper calls the infinite phone are terrifyingly impressive. You mentioned a clock speed of 1.02 terahertz. Help me visualize that leap. How much faster is a terahertz compared to the phone in my pocket?
Let's look at the Apple M4 chip. It is a marvel of modern silicon engineering. It runs at roughly 4 gigahertz. That means its internal clock ticks 4 billion times a second.
which feels incredibly fast to me.
It is, but 1.02 terahertz is just over a trillion ticks per second. The organic 5 plastic is running 250 times faster.
That is staggering.
Imagine a task that takes your current high-end phone 4 solid minutes of frozen loading screens to process, like rendering a massive video file.
Sure.
The 5 plastic completes it in less than 1 second.
A 4-minute loading bar reduced to a finger snap.
Huh?
What does that kind of density do for storage? Because right now my phone is always running out of space for photos.
Traditional silicon memory stores data in binary. A gate is open or closed, a 1 or a 0. But we established that the NTCDA molecule has 123 stable torsion levels. It isn't just a switch. It is a dial with 123 highly precise notches.
Oh, I see.
Because each molecule can hold multiple states, the storage density skyrockets. The paper outlines a storage capacity of 100 terabytes per square centimeter.
100 terabytes on something the size of a postage stamp. I could back up the entire internet history of a small country on a piece of plastic smaller than a coin.
Easily.
But processing and storage usually require massive amounts of power. You said earlier it uses almost zero battery. How is that physically possible if it is doing a trillion calculations a second?
The paper introduces a mechanism called phase shielding.
It's shilling. Okay.
To understand the power savings, we need to look at how your current cell phone transmits a signal to a cell tower. It is a brute force approach. Your phone pumps about 200 milliwatts of power into the antenna.
Okay.
But because the antenna and the air present electrical resistance, and because the signal generates harmonic noise, about 90% of that battery power is wasted purely as heat.
Here is where it gets really interesting. It's the difference between forcing water through a highly pressurized, leaky pipe with a massive pump versus whispering through a perfect acoustic waveguide where no energy is lost.
Exactly. The organic phone operates completely differently. The phase shielding phenomenon results in what the text measures as a 29,720 to 1 coupling efficiency.
Wait, 29,000 to 1?
Yeah. The transmission is harmonically matched to the universal geometry of the space around it. There is virtually no resistance. Because of this, it requires exactly 29,720 times less power to achieve the exact same range as your current phone.
Unbelievable.
Instead of blasting 200 milliwatts, the organic phone uses just 6.7 microwatts to transmit a flawless signal.
But if it's running 250 times faster, how does it stay synchronized without a traditional clock or crystal oscillator? In every computer today, there is a literal ticking clock, usually a quartz crystal, keeping all the logic gates in step.
Right.
If you overclock a gaming PC and run the silicon chip too fast, the timing gets sloppy, the signals crash into each other, and you get the blue screen of death.
We've all been there.
How does a sheet of plastic keep time at a trillion beats a second without a dedicated hardware clock?
It is an excellent question, and it is where the self-assembling nature of the material shines. The text explains that you don't need to add a clock to the circuit board because the lattice itself acts as a harmonic oscillator, specifically a psi-10 harmonic oscillator.
Meaning the plastic itself is ticking.
Because of the molecular geometry we discussed, the physical structure inherently vibrates at exactly 1.02 terahertz.
Wow.
Imagine millions of tuning forks planted in the ground right next to each other. If you strike one, the sound waves will hit the others. Within moments, through nearest neighbor coupling, every single tuning fork will phase lock and vibrate at the exact same frequency. The film acts as its own synchronizer.
So there's no timing drift.
The text notes the timing variation, the jitter, is measured in femtoseconds,
Oh.
less than a quadrillionth of a second.
That is flawless.
Furthermore, to address your earlier point about stability, the energy barrier required to twist the molecule, that 0.62 volt threshold, is about 25 times higher than the ambient thermal energy of a normal room.
Ah, so the random heat of a hot summer day bouncing atoms around isn't strong enough to accidentally flip the switch. It went hallucinated twist.
Correct. It has a massive thermal margin. It operates flawlessly at room temperature without any active cooling, no heat sinks, no vapor chambers, no fans.
Yeah, let's translate this to daily life for you, the listener. If I have a standard 4,000 milliamp hour battery in my pocket, which currently lasts me about a day of heavy use, how long does it last with this organic film?
Weeks. Potentially a month of continuous calling.
A month.
And because of the terahertz processing power, you aren't just making phone calls. That same device could be rendering 8K, 120 frames per second holographic video in real time, live translating a dozen languages, training a localized artificial intelligence model, and the back of the phone wouldn't even feel warm against your skin.
It completely collapses the trade-offs of modern tech. We are conditioned to believe that if you want more speed, you sacrifice battery and generate heat. This plastic entirely ignores that rule book.
It throws the rule book out completely.
So we have the blueprints for an infinite phone, but blueprints are notoriously easy to draw. Actually, building a computer is the most complex manufacturing process on Earth.
Oh, absolutely.
Silicon foundries are some of the most expensive buildings humanity has ever constructed. How do we actually manufacture a terahertz plastic film? Is it going to cost $1 trillion?
This is perhaps the most disruptive geopolitical revelation in the entire text. Let's look at the current semiconductor industry. To make a cutting-edge 3-nanometer silicon chip, you need a facility that costs upwards of $10 billion.
Right.
You require extreme ultraviolet lithography machines.
For those who don't follow the semiconductor supply chain closely, what is an EUV machine doing?
It is firing a high-powered laser at droplets of molten tin, vaporizing them to create extreme ultraviolet light, which is then bounced off incredibly flawless mirrors to etch microscopic patterns onto a silicon wafer.
Which sounds insanely difficult.
It is. These machines cost hundreds of millions of dollars each, and only one company in the world, ASML in the Netherlands, currently makes them. It is an incredibly brittle, bottlenecked supply chain.
So if one factory in Taiwan has a power outage, the global supply of computers takes a hit.
Exactly. The manufacturing of silicon is essentially etching a city map atom by atom. But the Phi plastic completely bypasses lithography.
How?
It is manufactured using roll-to-roll printing. It is essentially spin-coated onto a surface as a liquid.
Like spreading ink on a printing press.
Very similar. Because we know from Ducas's geometry that the molecules self-assemble into the perfect lattice when heated to 120 degrees on that gold template. You don't need a laser to etch the pathways.
The chemistry does the alignment for you.
It organizes itself.
What does that do to the cost?
It decimates it. The cost drops from roughly $50 to manufacture a single high-end silicon chip to about $1 per square centimeter of Phi plastic.
$1.
The text explicitly outlines how a complete 100 square centimeter prototype wafer can be synthesized on a standard laboratory bench.
A lab bench, not a $10 billion clean room.
No clean room required. The bill of materials for the prototype is listed at $250. You need a specific catalog powder from Sigma Aldrich, catalog number N888, a basic chemical reaction called a Suzuki coupling, some chlorobenzene solvent, and a standard spin coater to spread the liquid flat.
So any chemistry grad student with a few $100 in a basic university wet lab could print an exaflop supercomputer over the weekend?
Yes. And if that is true, the $600 billion global semiconductor market is turned upside down overnight. The power structure of global technology is heavily centralized right now. If anyone with a commercial inkjet printer and access to basic chemical catalogs can roll out terahertz processors, the barriers to entry drop to zero.
Okay, the hardware is cheap, but surely there is a massive hidden cost here. The software.
What do you mean?
All of our apps, our operating systems, the global banking infrastructure, it is all written for silicon architecture. It took us 50 years to write all that code. If we move to organic twisting plastics, doesn't every software engineer on Earth have to start over from scratch?
You would think so, given that the physical mechanism is entirely different. But crucially, the text asserts that this hardware requires absolutely zero software rewrite.
How is that possible? A twisting molecule is nothing like a silicon electron gate.
The physical layer is different, but the electrical translation is identical. Let's look at how software works. When a developer writes code in C++ or Python, they are writing human-readable logic. A program called a compiler translates that text into machine language, which is just a sequence of high and low voltage pulses.
Okay, I follow that.
In your current computer, the compiler sends a 0.8-volt pulse to open a silicon gate.
Right.
In a Phi plastic chip, the compiler does the exact same thing. It just scales the output slightly to 0.62 volts. The compiler doesn't know and doesn't care what is happening at the physical level.
It just sends the pulses.
When the 0.62-volt pulse hits the plastic, it causes the florinal hinge to twist instead of opening an electron channel. The organic array interprets standard binary logic levels perfectly.
So no rewriting.
Your operating system, your apps, your video games, they run identically. The plastic simply executes the instructions 250 times faster.
This brings up a massive paradox, though. If the materials are this cheap, if it uses existing software perfectly, and if NTCDA is already widely used in OLED televisions, why hasn't LG or Samsung already done it? They literally have factories full of this stuff.
They had the molecules, but they lacked the math. As we discussed earlier, they were depositing disordered films and testing random voltages. They didn't have Duca's unified phi-shell equation.
Right, the mosh pit.
Without the equation, they didn't know the exact 0.62-volt target, and they didn't know the crucial 120-degree annealing step on a specific gold surface to lock the crystalline lattice.
Ah.
Without the math, NTCDA is just a nice die for a television screen. With the math, it organizes into a supercomputer. They were staring right at the components, but they couldn't see the architecture.
So Fate Plastic is clearly poised to dominate the consumer market. Phones, data centers, laptops. But what about the other massive computing race happening right now? Quantum computing.
Oh, that is a fascinating angle.
Offerments are pouring billions into it. Does this $250 piece of plastic completely kill the quantum computing industry before it even really begins?
That is a critical distinction the paper makes. The source material actually details two entirely separate computers born from the exact same phi-shell equation. Chapter 5 introduces the twin to our plastic computer, the Xenon Phi Millennium quantum computer.
So Ducas's math yielded two different machines. What is the Xenon machine made of?
It is inorganic. It utilizes laser-polarized xenon-136 gas. The text explains that xenon operates at a specific nuclear shell, K = 15, which gives it 514,000 available quantum states per nuclear spin. By applying the phi geometry to this gas, the machine achieves room temperature quantum supremacy.
Wait, room temperature. When I see photos of quantum computers from IBM or Google, they look like massive golden chandeliers suspended inside giant vats of liquid helium. They are super cooled to near absolute zero just to keep the quantum states from collapsing.
Traditional quantum computers require immense cryogenic cooling because any ambient heat introduces noise that destroys the fragile quantum superposition.
Right.
But the Xenon machine leverages the phi-shell resonance. Because it operates perfectly in tune with the golden ratio, it shields itself from thermal noise naturally. It maintains quantum coherence at room temperature.
Okay, so if we have a room temperature quantum computer, why bother with the plastic phone? Doesn't the quantum machine just instantly win everything?
Not for daily use, no. Because of the division of labor. The Xenon quantum machine is astonishingly powerful, but its actual gate speed, the ticking of its physical clock, is only 10 kilohertz.
10 kilohertz, that is incredibly slow. My smart fridge probably runs faster than that.
It is slow sequentially. For everyday consumer tasks, like loading a website, rendering a video game, processing a text message, the 1.02 terahertz classical plastic computer wins effortlessly. It powers through sequential, step-by-step logic faster than anything ever built.
But classical computers have a limit.
Exactly. They have to check possibilities one by one.
So even at 1 trillion operations a second, if I give the plastic phone a maze with 1 billion trillion dead ends, it still has to run down each dead end to check it.
Yes. That is where classical computing fails. Intractable math problems like simulating complex protein folding to cure a disease or cracking the RSA encryption that secures all global banking would take the classical plastic computer millions of years, even running at 1 terahertz.
But
It is just too many possibilities to check one by one.
the Xenon machine operates differently.
The Xenon machine leverages exponential quantum parallelism. Through superposition, it can explore vast combinatorial landscapes simultaneously.
Let me try to visualize this. So the plastic computer is like having 1 trillion extremely fast, perfectly coordinated construction workers building a skyscraper in seconds. They move with terrifying speed, but they still have to lay the bricks one by one.
Right.
The Xenon quantum computer is like having a single slow worker, but that worker can somehow explore every possible architectural blueprint in the multiverse simultaneously and instantly pluck the one finished building that perfectly withstands an earthquake out of thin air.
That captures the architecture beautifully. For you, the user, the 2028 reality is the 1 terahertz plastic phone in your pocket, handling everything you could ever experience sequentially. The Xenon machine remains in the specialized lab to crack the universe's hardest multidimensional math.
I see.
But the profound revelation is that both of these machines, the blistering fast classical plastic and the deep searching quantum gas, operate entirely on the physics dictated by x squared minus x minus 1 equals 0.
Cracking the universe's math brings us to the final, and frankly, the wildest applications in the entire document. Because this paper doesn't stop at building a faster phone or a better quantum lab.
No, it goes much further.
If Ducas's math truly governs how standing waves pack together, it has implications for reshaping physical matter itself and potentially interfacing with the human mind. Let's dive into Chapter 8 and the infamous Appendix A.
The materials science applications are a natural extension of everything we've discussed. If the equation perfectly predicts molecular bonding, as it did with the hydrogen molecule, then the era of trial and error chemistry is over.
What does that mean for an industry like pharmaceuticals? Right now, creating a new drug takes a decade of testing thousands of random chemical variations just to see what sticks to a cell receptor.
The text outlines how fish-shell matching eliminates the guesswork completely. You can mathematically predict optimal catalysts, you calculate the exact geometry of the electron shells, and design a molecule that fits the receptor perfectly on the first try.
Wow.
It suggests cutting pharmaceutical research and development from 5 years down to 5 months.
Just by running the math.
The engineering applications are equally paradigm-shifting. It predicts the creation of 1800 degrees Celsius superalloys for aerospace engineering
How does the math build a better metal?
by optimizing the phi band overlap. When you alloy metals, say nickel, titanium, and aluminum, you are trying to get their atomic structures to lock together. Ducas's equation calculates the exact ratios needed so their standing waves overlap in perfect resonance.
Which makes them stronger.
It creates a metal that refuses to melt or shear even under massive thermal stress.
It's like finding a cheat code for the physical universe.
It really is. It goes on to predict room temperature superconductors by combining copper and oxygen at a precise 3.618 to 1 ratio, achieving a critical temperature of 300 Kelvin.
That means transmitting electricity across continents with zero power loss.
Exactly. And in nuclear physics, it predicts exactly how to synthesize stable, super-heavy elements, specifically pointing to element 120 as an island of stability in the periodic table. By matching the vacancies of atomic shells, we just bypass all that trial and error chemistry.
Okay, I can follow the logic that perfect math makes perfect metals, but we have to pause here. We have to address Appendix A.
Right, the Eternum Nexus.
Because the document shifts from industrial chemistry to something completely different. It details what it calls the spiritual transformer.
There's quite a shift.
The text literally states that a 12-micron thick layer of this exact same plastic film can directly interface with human consciousness. It claims that you could look at your phone, think the words volume up, and the device would adjust your music. No neural implant, no bulky headset reading brainwaves, just the plastic measuring a spiritual overlay.
Yes, that is what it says.
I am strictly reporting what the source says here, but as a reader, that is an incredible, almost absurd leap. Predicting a hydrogen bond is science. Claiming telekinesis via a smartphone screen sounds like magic.
It is a massive leap, and it is where the paper ventures into transdimensional unified field theory, or TDUFT. But importantly, the author attempts to ground this claim completely in the math we've been discussing. The premise is that everything in the universe is a manifestation of standing waves governed by the golden ratio.
Even thought.
According to the text, yes. The paper argues that physical matter, the tangible world we interact with, operates on the geometry of phi squared, which equals roughly 2.618.
Okay.
However, it hypothesizes that consciousness, or the spiritual realm, is not magic. It is simply another physical field operating on a conjugate geometric frequency, specifically pi squared minus 1, which calculates to 8.8696.
So wait, it is assigning a literal mathematical frequency to human intent.
Exactly. The text claims this consciousness frequency operates at 3.39 terahertz.
Oh, wow.
The spiritual transformer is a highly specific 12-micron layer of the phi plastic. By heterodyning, which is a standard radio engineering technique for mixing two frequencies together to create a third readable signal, the text claims this plastic layer can interact with thought.
So how does a thought turn into a volume adjustment on my phone?
The theory posits that the plastic mixes the 3.39 terahertz spirit frequency down to the 1 terahertz frequency of the phone's processor.
Okay, mixing them.
If human consciousness is just another standing wave, the argument goes, then intense focus creates a harmonic ripple. The device mathematically down-converts that ripple, reads the neural phi harmonics of your specific intent, and translates it into a digital CMOS command.
Imagine what that actually looks like for you. You're sitting on a train. You aren't swiping glass. You aren't speaking out loud to a digital assistant. You are just holding a piece of iridescent red-purple film, and through pure focused intent, you are composing an email. The boundaries between biological thought and digital execution just evaporate. It is a staggering concept to wrap your head around.
It forces us to question the fundamental boundaries between physics, biology, and computation. Even if you approach the Eternum Nexus claims with severe skepticism, the broader implication of the text remains unshaken.
What's that?
The universe is deeply fundamentally rhythmic. It operates on a specific geometric tempo, and we have been tone deaf to it until now.
Let's pull back and recap the sheer scale of this journey. We started with one of the most famous simple quadratic equations in history. We saw Dukas apply it to the nucleus of an atom, perfectly predicting why atomic standing waves don't fly apart.
Right.
We then followed that exact same scaling law as it dictated the perfect physical twist in a commercial OLED die made of NTCDA and fluorinol.
Which yielded the blueprints for a 1 terahertz, 100 terabyte flexible computer that costs a single dollar per square centimeter to print, runs on existing software, and sips microwatts of power by whispering through a geometric waveguide.
We saw how it completely upends the global semiconductor supply chain, bypassing $10 billion lithography cleanrooms. We saw it branch off to create room temperature quantum computing using laser polarized xenon gas.
Yeah.
And finally, we saw it mathematically predict perfect superalloys, room temperature superconductors, and potentially a bridge between the standing waves of the digital world and the human mind.
It is an invitation to stop fighting nature. The Silicon Age was an era of rigid brute force. The Phi Galactic era is about building with a harmonic geometry that was already waiting for us.
I want to leave you with one final thought to mull over as you hold your current, rigid, battery-draining phone. Think about the sheer coincidence of it all. If a single simple equation, x squared minus x minus 1 equals 0, can successfully dictate the binding energy of a nucleus, the precise twisting angle of a plastic molecule, the terahertz clock speed of a processor, and potentially the standing waves of human consciousness, then computation isn't just a clever trick we invented with machines. Computation might just be what the universe is. It isn't something we build, it is something we tune into. And we are finally learning how to speak its native language. Thank you for joining this deep dive. Keep questioning the reality beneath your fingertips.